Let's talk a little bit about section 5.3 inverse functions and just look at some things about them. So a function f has an inverse, or if it has an inverse. So if f of x has an inverse function g of x, then what is true would be that if f of x is equal to y, then g of y is equal to x. Okay, and then other ways to look at that is if I take f of g of y, I get my x back, so that original x, that I might be talking about. Here's some x, if it happens to be g of y, so I take f of g of y, I get back to x. And similarly, if I do that same sort of thing, g of y, well, y is f of x, so if I say g of f of x, I get back to y. And so that's stuff like, if f of x is equal to the square root of x, where x is greater than or equal to 0, and g of x is equal to x squared, where x is greater than or equal to 0, then these are inverse functions. And one way to talk about that is, if the square root of x is equal to y, then y squared is equal to x. All right, and you can try that with some numbers, right? So if the square root of 4 is equal to 2, then 2 squared is equal to 4. All right, so that's this idea with inverse functions, and it can get, I think, a little confusing because typically, we still use the of x idea. So we'll talk about f of x and g of x, but you really have this relationship between the ordered pairs, is that you can look here. What it does is it reverses the ordered pairs. So f and f inverse reverse ordered pairs. Okay, so that is if xy is on the graph of f of x, then yx is on the graph of, now, and here's where it looks funny, because I say is on the graph of g of x, right? But the ordered pair here is yx. So they're really being used in two different ways. So probably a better thing to do here would be to call those specific points x1 and y1, and then y1 and x1. And now it starts to look a little better, because now I can talk about f of x and the ordered pair x1, y1, and then just reverse them, and we have the ordered pair y1, x1, but that's still some function g of x, and so that's our inverse. Now, so what that looks like is, if I draw these things, so I'm just going to say, here's f of x, here's g of x. Then, if this is x1, y1, then I should be able to go over here and find the point y1, x1. And now, because of that geometry, we can see some things going on here. So, for instance, if we look at the slope of that line, I can get that slope by taking the difference in the second coordinates. So I could take y1 minus x1 and divided by the difference in the first coordinates. So that's x1 minus y1. And you see that's equal to -1, that slope. And so it's perpendicular to the line y equal x, because if I take two slopes, if m1 times m2 is equal to -1, the lines are perpendicular. Okay, so that's something from our pre-calculus days. So so we get this slope of -1, so I know it's perpendicular to y equals x. But then actually I know that y equal x, it's symmetric about that, and y equal x ends up being the perpendicular bisector of any of these lines I join between pairing points. And I can tell it's a perpendicular bisector because if I find the middle of this line segment, I'll see that it's on the line y equal x. So the middle of the line segment, again, I've got an x1, y1, and then switching those, I've got y1 and x1. To get the middle of that, the midpoint, I just take the average of the first coordinate and the average of the second coordinate. So that's x1 plus y1 over 2. And x1 plus y1 over 2. And so you see this is on y equal x. And so the midpoint here is on the line y equal x. And when I join those points, the line segment I get there is perpendicular to y equals x. So these two curves are symmetric about that line y equal x, and therefore we get this perpendicular bisector. Okay. Now, to give us an idea where this is going with calculus, notice that I can approximate the slope, right, at some x1. It's about the same as taking my x1 and oops, try that again. Oops, oh, there we go. Gosh, I lost where the stuff was. But anyway, so I'm gonna take 2 points here. So here's my x1, y1. And here's, say, an x2, y2. And so if I approximate that slope at x1 or somewhere in between or at x2, I can just take my y2 minus y1 over x2 minus x1. Right? There's an approximation for that slope, and as I shrink those down so that they're closer and closer together, I get that derivative. Well, similarly then, on G, so here's F, on G, I have a point here that's y1, x1, and another point corresponding to the x2, y2 that is y2, x2. And so if I want to approximate g prime at the y1, that is about, again, taking the difference in the second coordinates, that would be x2 minus x1, and then the difference in the first coordinates, that'd be y2 minus y1. But that is equal to 1 over y2 minus y1 over x2 minus x1. And so what we see is it looks like our g prime of y here is going to be equal to 1 over f prime of x. Okay, and so now the thing is that likely we would like to talk about g prime of x, probably, and so I can always swap the x and the y's at any time, and just knowing that well, I can call x y and y x, and so do I have this or do I have this? It actually doesn't really matter, right? I can give either f the y part or g the y part, as the independent variable. So I could also write this just as well as, so actually let me do a little more, talking about that stuff. G prime of y equals f prime of x, for y equal f of x. Okay, and but that's kind of hard to make sense of, actually. So g prime of y is 1 over f prime of y. So I kind of switched those, and so now I can look at it as, oh yeah, I've got my y. Actually, I misspoke there. Here I had them backwards, right? So unfortunately, I really need to write that as, well, let me erase all this stuff. Sorry about that. G of y equal x is how I want to say that. But down here, I can say it instead here. So I had f of x equals y, which is true, but I wanted to state it more that way. And so here I'd rather switch those and say, oh, well, that's g of x equals y. And so then if I rewrite this, this is g prime of x is 1 over f prime of g of x. Okay, and that's the big thing they're trying to get us to for those derivatives. And really it just comes down to our approximation. I didn't actually take the limit, I didn't use the limit sign here, but right, I could have, and as long as the inverse exists and so forth, as I let x2 go to x1, then y2 also has to go to y1, and so that's kind of the proof, and so we can get the derivatives that way. But notice that fraction is just this fraction, which then means, okay, yeah, I've got 1 over f prime. But again, we typically, like I did back here with the with stuff, right? I've got y equals the square root of x. Here, we wouldn't typically say y squared equals x. We would say x squared equals y, or y equals x squared. So that's this notation problem and communication problem that happens with the inverse functions, because we like to talk about functions of x as opposed to y, and we plot them that way with the x on the horizontal axis and so forth, but it can get a bit confusing, definitely at times with this, because of the fact that we're talking about two functions that reverse ordered pairs. All right, so I think of I think of a function like this, f of x, and another function like this, x of g of x. Okay, but what we see is that if I have this particular point on the graph there, then what I know is that this point, or a point on this graph, would match up as a f of x and an x for some particular x value, like a 1 and a 1, and here x1, f of x1. Okay, and so admittedly, I think it can be hard to keep track of at times with the inverse functions. Okay, so typically a good thing to do is do things like when you're finding an inverse function, so if I'm told f of x equals x cubed plus 3, and somebody says, well, find f inverse of x equals some function g of x. Well, typically what I would do is I would substitute a y for the f of x and write that, and then I would solve, again swapping the x's and y's. I would solve x equals y cubed plus 3 for y, and so I get y cubed equals x minus 3, or y equals the cube root of x minus 3. Whoops, 1 over 3. 1 x minus 3 to the 1/3, and so then I could say, oh, well, that's f inverse of x, which is also the same as what I'm calling g of x, and that's x minus 3 to the 1/3. Okay, so we'll stop there with this part of the introduction to inverse functions, and we'll do some derivative problems after this.